In this tutorial, I'll go over different strategies to visualize your shape model. Hi and welcome to Coding with Dennis. My name is Dennis. This here is the 7th tutorial in the series on how to create statistical shape models. So far, we only visualized our model through manual inspection in Scalismo UI, but a number of additional useful visualization methods exist. If you are to include your model on a website or in a presentation, I often find it much more engaging to make a small animation of how the model deforms. So a typical strategy here is to write the principal components from 0, move it up to 2 or 3 standard deviations, back to -2 or -3, and then to 0 again. And this here you'll do for the top principal components that you're interested in visualizing. Before diving into the code, let's look at the resulting animation that we are looking to represent. The first step is to write meshes to a folder for each small change to the model parameters. First, we define the values each component should take, for instance 0 to 3, to 0 to -3, and to 0 again. Of course, depending on your model, it might make more sense to only show ±2 standard deviation, as 3 standard deviation is quite unlikely shape. In the code here, I write these as integer values by multiplying by 10. So we put 30 as we want the components to go from -3 to 3, and 5 as it should capture every 0.5 change in the value. Next, we define the components that we want to capture. In this case, I want to capture component 0, 1, and 2. Then we create a function to write the steps to a folder. In the function, we simply loop over the range that we defined, apply this value to the selected component, get the mesh instance from the model, and write this to a folder. The next step is to load the mesh sequence into ParaView. So, to do so, select all the meshes from the output folder and drag them to the browser area in ParaView. To smoothen the visualization in ParaView, apply the Generate Surface Normals filter to the mesh. Next, set the canvas size to the dimension that you would like the animation to be in. This is found under View, Preview, Custom. In this example here, I set an image size of 800 x 800 pixels. If the animation view is not visible, enable it under View, Animation View, set the mode to Sequence, and the start time to 0, and the end time to the number of meshes in your exported folder, and the number of frames. You want to set that to the frame rate times the animation duration. So in our case, we choose a frame rate of 25 frames per second, and the clip to last 4 seconds, which means we set 100 frames in here. And now use the animation button on top to check how the animation looks like, and check that the mesh is positioned correctly in the scene, exactly where you want it to be. The last step in ParaView is now to export the animation. I recommend exporting it in PNG files and then converting those to a GIF afterward. Alternatively, ParaView also has a video export option. To export, choose File, Save Animation, select the name, folder, and in the animation options, remember to choose Transparent Background. Finally, we need to convert the PNG files to a GIF. This can be done using the program ImageMagisk. So with the terminal, cd into the folder with the PNG files and execute convert-delay 4-loop 0-alpha set -dispose previous, and then a star.png and whatever output file name you would like, .gif. This will create the final GIF file. Note here that the delay is in hundreds of seconds, so 4 is 0.04 seconds, meaning a frame rate of 25 frames per second. If the final animation here is not smooth enough, then go back and export a more dense set of meshes from Scalismo. Another helpful visualization technique is to show the point correlation in the model. For this, we'll select a point on the model and color the mesh based on the correlation with the selected point. This method here is also good to use when manually defining model kernels, just to have a visual overview of how the kernel look like. For this, we create a Scala mesh field instance, and then we provide a value to each point in the mesh. We'll use the absolute value of the covariance between the selected landmark ID and all the points in the mesh, in this case here. To begin with, we can try to visualize the manually created model. As the model was created with a single Gaussian kernel, we correctly see that the further we get away from the selected landmark point, the less the point correlates with this landmark. If we now instead use the created PCA model, we see that the kernel has incorporated that points on the mesh back side also correlate with the selected landmark point. The last visualization method I want to show is how we can visualize deformation fields. This method here is useful to check how smooth the deformation fields of a model are, as well as debugging corresponding estimation functions, such as the ICP function. We select two instances of the model, in this case the reference and a random sample. Then we calculate the deformation vector between these two meshes. As both of these instances are from the model, they are in point correspondence already. And finally, we can visualize the deformation fields in Scalismo UI and change the color values of the deformations based on their amplitude. So, in summary, always visualize your models and try out different visualization methods to better understand the inner working of your model. That was all for this video. Remember to give the video a like, comment below with your own shape model project, and of course, subscribe to the channel for more content like this. See you in the next video.